What if the most important computer in the next decade isn't sitting in a data center at all, but orbiting 200 miles above your head, making decisions before a single human ever sees the data? That's not science fiction. That's the plan China just put on the table, and it changes the terms of the AI race in a way almost nobody outside a small circle of space engineers and defense analysts has fully absorbed yet. For years, the story of satellites was simple. A satellite looks at something, a ship, a coastline, a wildfire, a missile launch, and it sends that raw information down to a ground station on Earth. Humans and computers on the ground then sort through it, decide what matters, and act. That pipeline worked fine when there were a few hundred satellites in orbit sending back modest amounts of data. It does not work when there are thousands of satellites, high-resolution sensors, and radar systems generating more raw information every day than any ground network can absorb. The bottleneck isn't in space anymore. It's on the ground, in the narrow pipe trying to funnel an ocean of data back down to Earth. China's answer is to stop treating that pipe as a solution and start treating orbit itself as a place where computing happens. In late July 2026, Baidu AI Cloud announced a partnership with a Shanghai-based space computing company called Zhongke Tiansuan, sometimes known internationally as ComoSpace. The deal was signed at the CCF Chip Conference in Beijing, and the goal, in plain terms, is to build what the companies are calling an integrated space-ground intelligent computing ecosystem. Baidu brings its cloud architecture and its AI models. Zhongke Tiansuan brings the hardware, computing systems specifically engineered to survive the radiation, the temperature swings, and the power constraints of space. Put those two things together, and you get something genuinely new. An attempt to run real AI models, not just simple filters, directly on satellites while they're in orbit. Here's why that distinction actually matters, because it's easy to hear AI in space and assume someone just bolted a laptop onto a satellite. That's not what's happening. The idea is closer to building a cloud service, the kind of infrastructure companies like Amazon or Microsoft run on the ground, except the servers are flying at 17,000 miles an hour. If it works the way China's engineers describe it, satellites wouldn't just collect images and beam them home. They'd analyze those images where they're taken, identify what's actually significant, and only send the important conclusions back to Earth. A satellite watching a shipping lane wouldn't transmit hours of raw video. It would transmit unusual vessel movement detected. Here are the coordinates. That's the difference between a camera and a brain, and it's the difference this whole initiative is built around. China has laid this out in 3 layers, and each one solves a different piece of the puzzle. The first is the technical layer. Cloud-native software, large AI models, and autonomous agents running on hardware that has to survive an environment nothing on Earth prepares you for. Engineers working on this have talked openly about the twin nightmares of space computing: radiation that corrupts chips and causes silent errors, and heat that has nowhere to go because there's no air in orbit to carry it away. Solving that means redundant systems, error correction built into the hardware itself, and in some cases, experimental cooling loops that move heat through fluid rather than airflow. The second layer is the platform, a unified space cloud service designed so that a user on the ground, in theory, could request computing power or AI processing from orbit the same way you'd spin up a server on Amazon Web Services today. And the third is the application layer, the actual jobs this system is meant to do: emergency response after disasters, tracking ship movements across contested waters, and inspecting energy infrastructure like pipelines and power grids from orbit in near real time. Now step back and think about what that third layer really means once you connect it to the first two. A wildfire spreads fast. A ship changes course suspiciously in the South China Sea. A pipeline shows signs of a leak. In every one of those cases, the value of the information collapses the longer it takes to reach someone who can act on it. If a satellite has to beam raw data to a ground station, wait for a human analyst, and then relay a decision back out, you're talking about a delay measured in hours, sometimes longer if the satellite isn't even in range of a friendly ground station at that moment. If the satellite can process the data itself and immediately flag what matters, that delay shrinks toward real time. That's not a minor efficiency gain. That's the difference between catching something as it happens and reading about it afterward. And this is where the conversation stops being about convenience and starts being about power. Faster processing in orbit has obvious value for things like disaster response, but the exact same capability is just as valuable, arguably more valuable, for intelligence, surveillance, and reconnaissance. A network of satellites that can independently detect and classify ships, track troop movements, or process radar imagery without waiting on a ground link isn't just a scientific achievement. It's a faster, harder to disrupt sensing and decision layer for military and strategic use. And there's a second piece to this that gets less attention but matters just as much: dependence. Every ground station is a potential target. In a serious conflict, communications infrastructure, data links, and terrestrial facilities are exactly the kind of thing an adversary would try to jam, hack, or physically strike. A satellite network that can keep functioning, analyzing, and making decisions even when its link back to Earth is degraded or cut off entirely is a network that's much harder to blind. That resilience is a strategic asset in its own right, independent of anything about speed. To be clear, none of this means China has already built a functioning AI-powered network across space. What exists right now is a mix of demonstrations, early deployments, and an announced partnership aimed at scaling something that is currently limited. Zhongke Tiansuan has logged real orbital operation time with earlier hardware, and there have been demonstrations of large language models running on satellites, including one instance of running an existing open model in orbit for the first time. But running a model as a proof of concept on one satellite is a long way from an operational network space cloud that soldiers, companies, or emergency responders can actually rely on. The Baidu Zhongke Tiansuan partnership is a serious step toward that future, not a declaration that the future has already arrived. The United States, for what it's worth, is not standing still on this either. American companies are exploring space-based data centers and orbital computing too, and some of that work is genuinely cutting edge. But the driving force behind most of it looks different. It's largely commercial, pushed by private space companies and venture-backed startups chasing a very specific terrestrial problem. AI data centers on Earth are running into limits on electricity, land, and cooling, and space starts to look attractive as a place with unlimited solar power and no shortage of cold vacuum to dump heat into. That's a real and rational motivation, but it's fundamentally a business-solving and engineering constraint. China's version of this story reads differently because it isn't just a business trying to solve a cooling problem. It's one more piece connected to a much larger national strategy that already links satellites, telecommunications, semiconductors, AI development, and information infrastructure. When a government treats orbital computing as part of the same strategic picture as its chip industry, its satellite constellations, and its broader AI ambitions, that's not the same kind of project as a startup chasing cheap cooling. It's infrastructure being built with the state's long-term interests in mind, and that changes how seriously the rest of the world should be watching it. Which brings us to the real question underneath all of this. For the last few years, the AI race has mostly been framed as a contest over who builds the most powerful model, who has the most advanced chips, who trains on the most data. That framing missed something. If computing itself starts moving into orbit, the next competition might not be only about who has the smartest model sitting in a data center. It might be about who owns and controls the infrastructure that collects, filters, and delivers information from space in the first place. The layer that decides what data even reaches the ground and who gets to act on it first. Satellites spent the last 70 years as passive observers, cameras in the sky, waiting for someone on the ground to make sense of what they saw. What China is now building toward, carefully in stages, with real engineering obstacles still unsolved, is a version of space where satellites stop waiting and start deciding. Whether that vision fully materializes is still an open question. But the country that manages to build it first won't just have better satellites. It will have a head start on controlling how the rest of the world sees and reacts to everything happening on the planet beneath it. And that might turn out to be a far bigger prize than anyone building AI models on the ground ever imagined.